Welcome to the last lecture in mathematical finance for this term. So what we want to discuss and study today is how one can go from the discrete time setting, which we studied during the whole course so far, to the continuous time setting, which is then the setting in which we want to work in the advanced mathematical finance course. As I promised you at the end of the last lecture, this 25th lecture will not be examined. So as part of the course, I hope you all watched the video as motivated as the videos before, but I will not ask any questions in the exam concerning this lecture. So this is chapter 8. And today, I don't want to torture you in the last lecture with heavy calculation, so I will drop many simple but lengthy calculation to more provide you what's going on and explain what's going on. You can look in the lecture notes for more details as you want to. So, okay, what's the goal for today? That's chapter 8. From discrete time setting. So discrete times means our index set had these t time steps, and continuous time means, okay, the time is modeled by some continuous set, so some interval from 0 to t where you can pick any point between 0 and t where you can trade and where you have a asset price available. If you think about real financial markets, this is actually somewhat realistic model. If you have these million microseconds in which you can trade, it's a reasonable way to say, okay, this is basically continuous. And there are many advantages also to look at the continuous modeling, because it gives you closed form solutions for a certain price and certain models. You have nice PDE characterizations, and then or numerics for stochastic differential equation and PDEs, which are then available, and you can use them to calculate your hedging and pricing strategies, your optimal investment strategies, and so on. So all the things we have considered or discussed so far, you have continuous counterparts, and they often look actually nicer than in the discrete setting, at least from a mathematical point, nicer. So what I want to use here is the simple binomial model, which looks very simplistic because the prices can only move in an upwards direction or a downwards direction. And you can say, oh, that's a bit simple. Why should I use this to model a financial market? Because it might be unrealistic to say that the price can only, the next step, take two values. But I would like to convince you that this is actually a rather natural setting, because we haven't restricted ourselves to small number of time steps. So the idea is we want to use more and more time steps, and this means there are also more and more price movements on the market, and this in the end leads to a rather complex and fairly realistic model. So at the end of the lecture today, we will see the famous Black-Scholes model, which were the initial work which really made these financial derivative markets profitable. So right in the beginning of the 70s, people understood, and Black-Scholes, Merton, these three guys, they understood that this how to mathematically rigorously price options, and this was then open the market for financial derivatives, because there was a reasonable way to trade and price these objects. Okay, so continuous time means I consider an interval now from 0 to t. So t is our terminal time as before. and I fix it for today. So we still have a maturity time, capital T, as before, but now we can trade at any time. So continuous. And what we want to do now, I want to take my interval. Oh, that's this is my interval 0 to t, and I want to divide it into steps of length 1 over n. I mean these equidistant steps, as you can see. So this is at the length 1 over n. So we want to divide this into n time steps. So divide the interval 0 to t into n time steps of length, well, now you won't be shocked. The length of these time steps is called delta n. It's just given by capital T divided by n. Okay. So these are our time steps. And the idea is, I mean, okay, if we make this grid fine enough, we might have sorry, we might end up with some fairly continuous model. All right. So I want to allow myself to be able to trade at each of these time sets which I've shown. So I have basically a continuous world, but say I can only trade at these fixed time steps. And well, n is of course here a natural number. And now we want to consider the corresponding binomial models. They depend now on the length, step of length we decided. So we have here market with n trading periods, right? And well, these binomial models, I mean, they're here. Right, so these are our models. In this world, I mean, we say that this is our standard binomial model. So what does this mean? Our risk-free asset is usually given by the interest rate Rn, but I mean, if the time length gets smaller, we want to adjust the interest rate as well, because this means this is Rn is the interest rate we get over this smaller getting periods, right? So we need to, I mean, adjust it. Right, so let's say we have our n step model, so n periods. In each of this time step, we get an interest rate Rn, and this is the growth rate as we had before. Well, we make our life simple. We consider a one-dimensional setting, as we often did in the binomial model. So what is the price, the k step here? Well, the usual idea to model it, so this depends on the price movements in the kth period, and of course the price given at time k. So this is, I mean, what you have seen. I mean, this is a standard model. We just have this extra index coming from that we have actually in the end a sequence of models. And then we have here again also our movements. So the upwards factor depends on the number of the lengths, right? And the downwards factor also depends on the lengths, and we say, well, with probability P this appears, and otherwise this appears with probability minus P, right? This is and to be honest, I mean, I have to also fix where we start. And when the price at time zero, the price is known, so they assume to be, I mean, the same for all models, right? Because well, it's the price we observe currently, and we observe a negative price. Okay. Okay. So, okay, K is N. And well, the construction we have, I mean, this is the discussion we have discussed at least once. So these YNs modeling the upwards vector and the downwards vector, I mean, it depends not only on the time length of the chosen model, and we also assume that it's mutual independent. So this is right. Okay. I mean, you can also amuse yourself, but I think this is because we know that this physical probability P is not super important. I mean, you could make them also dependent on N as well, but I mean, this doesn't change anything because we anyway, what we want to do is always only depends on the risk neutral measure, and the risk neutral martingale measure is independent of the exact value of P. I mean, it's not independent of the underlying physical measure because the underlying physical measure determines the null sets, right? Because we wanted to have an equivalent martingale measures. But the moment the null sets are determined, it doesn't matter which exact value this P takes. Okay. And now, okay, for R and parameters. Okay. And of course, this all has to live on some probability space and so on. So this is here, we have the sequence of binomial models, which depends on, okay, we want to make our grid finer and finer. And the question we want to study today is what happens if we send our n to infinity. So that's, so what does it mean here? If we send n to infinity, this means, okay, we allow to trade faster and faster. So if we make this grid finer and finer, and have the hope that, well, even if we have a simplistic model, which just two price movements, the instant where the price can move gets infinitely small, so this becomes a rather complex model. So that's actually the simple question we want to do. So what happens if we make the grids and the step size going to 0? So what happens with the model, and what happens to the prices of, for example, for European options? I mean, because if we price an option in this binomial model, and we make the approximation, for example, in America, one finer and finer, what happens to the prices? Okay. Okay. So Well, so you all well trained in probability theory. So there are some tools to study exactly such a situation where you have a sequence of random variables and you want to understand what's going on. And let me make you here a heuristic observation. Make it green. The heuristic observation is okay, that's almost. If you look at the terminal price, so I mean, we have actually a sequence of processes, right? We have discrete time processes, our binomial model. But in order to study processes, I warmly recommend you to visit the course Wahrscheinlichkeitstheorie 1 next semester. So we need to keep it here a bit more simple. But of course, you can make this much more sophisticated what we are doing here. So look at the price of the nth binomial model at the terminal time. So this is n is the terminal time. So what is this? This is t and t. So the t terminal time. Oh, what's going on? Why is here is t and oh sorry. Sorry. Sorry, here's here k is okay, but here this is of course okay. Right, okay, let's make it here t. Oh, sorry. Right, so you look at the nth model, and I want to have green. Right. Okay, I take the logarithm of the terminal price in the nth model. Why do I want to take the logarithm? I mean, because the price here at time 0 is always the same. And what do I get here? So the terminal price in this model is just given by the logarithm, the sum of the logarithm of the price movement each period. Okay. And this here are independent and identically distributed random variables. Look, I mean, these are the right case, and if you take a continuous function, you keep still the same, the independence. And let's label this. And now you think what you have learned in probability courses, so in Stochastic 1 and Stochastic 2. What is this? Well, this is the sum of independent random variables. So I know if I scale it right and normalize it in the right sense, that's a central limit theorem, which tells you, oh, this actually, by normalize it in a smart way, converges to the normal distribution. And this is actually the tool we want to use to understand what's going on for to understand what's going on if we send the n to infinity, right? So this is central limit theorem. And I want to use the version due to Lindenberg Feller. So I hope you have seen it at some point. If you haven't, don't worry. Today, I will not give you any technical details. So you can look at the proper formulation of this theorem in the lecture notes. And or look in the book of Klenke, where you can find the proof, if you haven't, or if you want to recall the proof. So what's the statement? Oh, if I have suitable conditions on my which you have to check. Don't worry. I mean, lecture notes give more details. So under suitable conditions, what do we have? We have the probability. We have a sequence AN. If I take such a sum of random variables, which are independent, and I subtract the mean, and I divide by the variance, this goes, if I take the limit n to infinity, to the difference of the distribution function of the normal distribution at the point alpha minus the point beta. So if, and this is a sequence of real numbers, and they alpha n converges to alpha and beta n converges to beta. And to make this somewhat reasonable statement, we assume that alpha is less or equal than beta. And as we know, you use it later. I mean, we have seen it already. So this phi here, this capital phi, is just the normal, the distribution function of the normal distribution. Normalized, so standard normal distribution, so with mean 0 and variance 1. All right. Bit hand waving, but this is something what you need if you look at these prices and you see, oh, actually this price, if I just take the logarithm, I have actually a sum of independent and identical distributed random variables. So if I want to understand the convergence of it, the central limit theorem is one way, or the tool we want to look at. Okay. Okay, let's come to the question in orange. Okay, what happens if we let send n to infinity? Chapter 8.1. Let's, okay. So what we want to do is we want to start to study two things. First, we want to understand what happens with the option prices if we send n to infinity, and then we want to understand what happens to the models, because this is actually even more complex if we send n to infinity. Right. Okay, one thing I need to specify if I want to talk about convergence of anything is I need to tell you what are my parameters in the models I take. Of course, this is, you have freedom to choose different ones. but you want to choose them smartly that it works. So it depends on the choice of parameters, whether, I mean, how these binomial models converge. And of course, numerically speaking, you want to think to find a rather smart way to choose them. I'm not saying I choose them numerically smart. I choose them smart in a way that I have not so much work to do. And this is the first smart choice I make. So my interest rate, Rn, is just given by an interest rate, so the exponential function, and then I multiply with the length of the interval. Because if I mean, this is, if I plug it in, as we see later in the definition of our interest rate, well, I always get this exponential function. And now I define the upwards movement. This is again, okay, I take my exponential function, I introduce a parameter sigma, and then here I scale it in the smart way by taking the square root of the length. The upwards movement is just 1 over the downward movement. So this is minus sigma times the square root. I mean, this scaling is, of course, it means it's not random, even if it looks random for you. But I want to have here the square root. I mean, this is what you, so if you study the Brownian motion, the scaling, you will understand. I mean, I will tell you what the Brownian motion is later, but you will learn it in the course. Wahrscheinlichkeitstheorie 1. Sorry, I haven't specified. All right, so this is my one parameter and this is my interest rate. Okay, now I can specify parameters, and you all know if you want to talk about the pricing and hedging of options. So here we only talk about pricing, but you can also consider the corresponding hedging strategies. We want to have arbitrage-free models. This was what I'm telling you all the time. If you want to do pricing and hedging of options, you need to have an arbitrage-free model first. And these parameters might actually violate this condition, but what you can check, if we make n sufficiently large, then we have our no arbitrage condition. So the downwards movement is strictly less than the returns in the risk-free asset, is strictly less than the upwards movement. And now we know, well, if you have these conditions here, this means that my model, so at some point, I mean, I need to consider big enough if n, but after that, all my models are arbitrage free. So we have here actually a finite market, only finally many movements, and this market is arbitrage free. If our market is arbitrage free, so if the binomial model is arbitrage free, we also know that it's even complete. Okay. Cool. And well, we even want the unique equivalent martingale measure is Q is Q depends on which model we have. Qn is given by okay. So you can go back to the section of the of the binomial model. So we discussed this, we calculated the model here. So this is, I mean, I'm not redoing the calculation, but this is a good moment to go back and verify that I didn't do a mistake copy pasting this formula. Okay, so if you want now to price an option, interesting. What can we do? So another thing we need to recall here, if we have an option, European option, derivative psi given by the terminal price here. So, so what is the price? The arbitrage free price is, so that's pi of psi. Okay, we have our discounting factor beta t, and okay, this beta t depends on n. And then what was this price? So you count the path how you get to this Sn at the terminal mt, and then you multiply it with the probability that this path appears. So this is our risk neutral measure, which you need to price. You need to use to price an option. And you have f, and this is nothing else. So the terminal price here is the initial product multiplied with the upwards movement which occurred on the market and the downwards movement we have. So this is with, I mean, yeah, this 1 over k, the binomial exponent here. So just to recall it, that's what it is. All right. And also this formula, I mean, should not be new for you. This is derived in the corollary 4.19. So if you're shocked and you say, oh, I haven't seen it, go back in the lecture notes and verify that I didn't do a copy pasting mistake. All right. So what is now, well, what's the observation if you let n to infinity? Let me give you directly the theorem. And this is theorem 8.2 in the lecture notes. Okay, what's the statement? Let us, I mean, consider a simple case, namely the call prices, because I mean this is one of the main examples of traded option. So let us consider the call price at time 0 in this end model in the arbitrage. For a price of call option with maturity T and strike price K. Okay. K is positive strike price, maturity okay, T. in the market N K S N K N. Okay. So this is, okay, the moment you know how the call prices you converge, you can use the put call parity to understand also how the put prices converge, and this is actually the main thing we care currently about. To put in call options. Of course, you can ask, hey, what happens if I get more complex pairs and so on? Well, then the analysis gets more complex. What's the statement? Yeah. If I look at the limit of n going to infinity of the core prices, they converge to the following object. So I have the initial value, then I have my distribution function evaluated at some point, and this point, I can tell you what d is. D is for here plus okay, that was not good. Here we are. This is my log again, divided by sigma and t squared. Okay, then that's d minus k discounted, and then the normal distribution evaluated at time d minus. All right. That's okay. So that's, and this is what we understand. I'll explain this in more details at the end of the lecture. That's the Black-Scholes formula. So the price of a call option in the continuous setting corresponding in the end to the Black-Scholes formula, Black-Scholes model. Anyway, all right. So this is, and what we see is here, if we take the call options, so the prices of a call option, simple call option, in the Binomial model, we choose the time steps which we use to model the reward smaller and smaller. Then we end up actually with the continuous limit. And the continuous limit is, as we see in the end of the lecture, the price in the Black-Scholes world. Here. So feel free to look in the lecture notes to check out more details. Proof. Actually, if you really work out all the details, the proof is rather lengthy. But this is okay. It's a complex convergence analysis here. But for us, is okay. We look at we know all the call prices. If we plug into what we look at this formula, which we call now 8.2 as an lecture note. So we look at we look at this formula, and in the end, we just need to understand towards this formula converges. So let me introduce the number an, which is the minimum on k. K is a natural number, it might include 0, such that I have enough upwards movement in my market so that I'm above the strike price. So these are all, so and this is the minimal number of upwards movement I have if I look at my binomial tree. Okay, that's not what it looks like. Right, like something like this. So this is my binomial model, how it looks like. And now I ask for the set. If I put here my strike price K, okay, how many upwards movement do I need to be above K? Well, I need probably at least one. At least two. Sorry, at least two upwards movement, because this looks higher, right? So if K is like this level, then it's two upwards movement. So this is my minimum. Okay, so setting like this, you get from 8.1, right? So we'll go back to our formula, which gives us the price of a call option in the nth model. Well, here our function f, here this function is now given by our call price. So we can plug in this and the definition of an to get the following. Right, so you get K, and you start now summing by the number an. And now here you have a definition. You plug in your upward movements. Right, so you have at least K upwards movement here, so you can put these together, and now you have n minus K downward movements, and right, you have your discounted. Here's you have tried the discounting factor. This is your B and T. And here again. So I mean, because all the K's which are less than an, I mean, they're 0 anyway, so you don't need to start summing there. Right. So this is okay. A minus K. And so this is, so basically you use that, you know, if you are bigger than an, the function is just a linear function, so the prices are always bigger than K, and otherwise you're 0. So this is the amount you get from the price, and this is minus the strike price and the probability that you're in this scenario. That's nice. So this goes to Sn. This is also simple. As n goes, as 0 goes to S0, I mean, if you send n to infinity, yeah, you're hopefully on my side. This is also not too hard. So here you just need to plug in the definition to get this. So the exponential function to the power minus RT. And this is a bit harder. And bit means significantly harder. Here you need your central limit theorem, which tells you, oh, this goes actually to the normal distribution at the evaluated d. This, you can again use your central limit theorem to show that this goes to the normal distribution at d minus sigma times r. And this is non-trivial. Right? This is, I give you a sketch in the lecture notes which has more than one page, and there are still missing details. That's nice. And now, that's it. Like you see, on the structural level, this is actually not super hard. Now you go upwards to see your X-Coles formula again. So the limit of the core prices in each model, I mean, this is Sn as 0, S0 here, normal distribution at point D, strike price minus strike price, discounted by the interest rate, and then the normal distribution evaluated at the point D minus sigma p. Nice. Okay. So, okay, this is what happens to the core prices, and now let's study what happens to the models. So the sequence of binomial model. And this will bring us to the famous Black-Scholes model. Okay, let's start with the simpler one. And this is the risk-free asset. And so here if we assume that our Rn, and this is what we did, is given by the exponential function Rn minus 1, what do we get? The n at the terminal time t is given by 1 plus Rn to the power n. Well, we just plug in the definition here, and luckily we took it in a smart way that we exactly get the exponential function of RT, right? And this is as n goes to infinity stays constant, so this is true. So this is actually not the really statement, but okay. If you take n to infinity and we stay always constant to the exponential function RT, I mean, the limit is also this. Okay, that was super simple. And now let's look at the risky asset. Right. Oh, such a green mess. Okay, what happens here? Okay, here it gets a bit more complex. Here you need again at least the central limit theorem, which I just stated. And this is so here, I mean, the convergence takes only place in distribution. Convergence in distribution. And this goes to S0 multiplied with the exponential function of sigma times Wt. Okay, wait. Wt plus r minus 1/2 sigma squared t as n goes to infinity. Now I need to tell you what this Wt is. So Wt is a normally distributed random variable which has a distribution 0 at the mean 0 and the variance t. Why should you believe me this? So this is again the idea, okay, here you find the central limit theory. Okay, why should you believe me this? Well, let's go back to our heuristic idea we started with here in green. If I take the logarithm of my binomial prices, the price in the binomial model at time t, where I have a sequence of random variables. So I get a sum of independent random variables, which converges to the to some normally distributed object, right? And if I look here, so if I take here the log of the binomial model, I converge to something. So if I take the log of both sides, I know this goes to some normal distribution, and the normal distribution actually given here by sigma times the random variable, which has normally distributed with mean 0 and variance t. And then I need to move the mean to the right point. And the right point is actually the interest rate minus 1/2 sigma square multiplied with the terminal time. And now I need to reverse my taking the log. This means I take the exponential function of both sides, and by the continuous mapping theorem, this again converges. So we have here that the price in the binomial model converges to something which is exponentially normally distributed. All right. Now I make a slight gap. This brings us actually to the black skulls model. So what is the black skulls model? So the interest rate at time t, so the risk-free asset at time t, so this is a model in continuous time, means we have a stochastic process which is indexed by now a continuous time set. And the risk-free asset is given by the exponential function times an interest rate t. Right? So the growth rate is given by the interest rate, and then it's the interest rate growth exponentially, as you have seen in probably some courses or in school already, that this is the natural way to model it. And I mean, if you look at here, how we did it, this is actually true. I mean, we only discussed it here at the terminal time, but you get the conversion at each time point. A bit more complex is the following. So that the price of the risky asset is assumed to be the exponential. So you look at this formula we derived here. Now we replace the terminal time t by any time t, small t, to get the following definition. And this is actually the binomial model under the martingale measure. Q, where we have our, so the dynamic is actually, we derived here is actually already given under the equivalent martingale. So if you have a measure Q which looks at this dynamic, the moment I tell you what this WT is, you can verify that this is a martingale. And this is what you already can verify by the knowledge you have. So R, the interest rate, okay, and sigma is called volatility. So the volatility on this market, it measures how heavily the price fluctuates on the market. And usually when if you have prices, the fluctuation goes more heavily, and if you have a calm time, then fluctuation of the market gets low. And this is, it's a very important parameter for the pricing and hedging of assets, of the differential derivatives, but okay, we need to estimate it somewhere. And now I need to tell you, and WT, it's now a stochastic process in continuous time, but here you don't need to be scared. It's just you place the index set, which was for the strip T by a continuous index set. That's fine. Is a so-called Brownian motion. Okay. Okay, now I know you will say, what's a Brownian motion? Okay, I'll give you the definition. The definition, I'm not there to give this a number because I do not prove anything. So stochastic process so it's continuous time, is called Brownian motion. If there are four properties. First one, we start at 0. That's simple. Second one is we have independent increments. As independent increments. Okay, what does it mean? If I look at here, if I take any points ti and look at the increment from ti to ti plus 1, this is a sequence of increments, and they are assumed to be independent. Right, this is just a selection, a finite number of random variables, and you know what this means, that they are independent. Third property, the increments. Okay, now you know what increments are. Increments are stationary and normally distributed. So what does this mean? So if I look at the increment of the Brownian motions of w at time t minus w at time s, the distribution is given by a normal one, and the mean is 0, and the variance is just given by the time increment, so t minus s for stn. So this is all what it means. Stationary means it doesn't matter where you take an increment, the length of the interval determines the distribution. One final property is w t as almost surely continuous path, sample path. Again, what does it mean? So if I look at the function, this is continuous for almost all omega in omega. Right? Okay, so nothing scary. The only thing what one needs to do, and this is okay, what you understood all by now, is it's not trivial actually to guarantee that such a process exists, right? So the construction of random variables was a lot of work, and also the construction of stochastic processes gets rather complex. And I mean, to just say, okay, this is actually a nice way to model financial market. Well, in the end, as a mathematician, you also want to verify that the mathematical tools we use, they're reasonable and that they exist and they make sense. So that's a non-trivial task, which you, as I understood it, you will consider there's such a Brownian motion, so such a stochastic process exists, I mean, will be proven in the lecture. Of course, this is Wahrscheinlichkeitstheorie. Wahrscheinlich. Theorie. Right. So next term, if you're interested and you want to very ensure that such a Brownian motion exists, that's one topic you will see. Okay, so but here we assume we have this object. So that's our model, and it's not hard. So that's our Black-Scholes model. And this is a rather helpful way to model a financial market. Okay, if we now work, and this will what we do, start studying in the advanced mathematical finance courses. If you want to write such a model in discrete time, in the end, you need to do similar things, or you start similar things, even if this is not our priority in the advanced course. Your first thing is you need to check that this is again an arbitrage-free market. You need to verify, generate the definitions we have to this situation. Here, I'm not going to do this. It turns out the Black-Scholes model right? This is our market, is arbitrage free, and complete market. And this is actually exists a unique equivalent martingale measure Q. Well, and this is, I mean, again, so there are versions of the first and the second fundamental theorem of asset pricing, which allows you, again, if you have a certain class of underlying models, which are called semi-martingale, so this is a continuous time object, and then we can characterize the arbitrage freeness and the completeness of a market in terms of the existence of a martingale measure. Okay. All right. So if we now in this Black-Scholes setting, Black-Scholes, well, this is Black-Scholes model, the price of arbitrage-free price. So I mean the ideas, of course, I mean the conceptual ideas we developed in this course, I mean they're not wrong in the discrete setting, right? The continuous setting. So the ideas, the tools and the mathematics is complex, more complex, but right, then the meter ideas are still true, or still work. So the arbitrage-free price, let's call it C Black-Scholes 0 of the call option. Right, this is the call option, so you have the right to buy an asset for the strike price K at the terminal time T is okay, Black-Scholes. Let me scroll down. So what is the Black-Scholes price of a call option? Well, it's the discounted expected value under the martingale Q of the payoff of the option. Right. Okay. This is, I mean, this is a formula you have seen in the binomial model as well. So that's still true. The continuous time world, and this of course the terminal time of the risk-free asset. But now you have your continuous formula. Well, actually you're in the nice setting. You know all the you know the distribution, the price at the terminal time, right? This is just given by a normal distribution. That's why you have right? So you take the exponential. This is an exponentially distributed normal random variable. So let's take the exponential of a normal variable z, which is normal distributed, and then you plug in the coefficients you have. This is, I mean, it's not, I mean, what I'm doing here is it's not magic, right? It's just looking at the terminal time of the price at the risky asset and thinking about what the distribution is. Mm-hmm. In terms of the normal distribution, right? Square. This is the mean. And you have here power 2. Here you have a bracket as well. Divided by 2. Right. 2 sigma squared t. You have here exponential function. This is an integral with respect to dz. There's a 2 missing. Sorry, now I'm confused. Right. Be careful. Be careful. Right. All right. All right. I hope I didn't do a mistake here. Anyway, so what you can then do some calculation and calculate this expression here further. And what you get is exactly what we have seen already, namely a 0. And it's coming here. Exponential. And this is right. This is, as I already claimed, this is the Black-Scholes formula. So the call price in the Black-Scholes model is given by exactly this formula. And for us, with them in the knowledge where it's come from, it's just the expected value under the risk mutual measure of the discounted payoff. So in other words, and this is what we have seen so far, if you look at the call prices in the binomial models, the sequence we defined, they go to the Black-Scholes price. Right. And so this is more summary. The binomial models, they go to the Black-Scholes model, at least in distribution. And you actually can make this even more sophisticated to look at functional central limit theorems to show that really the path converges in a distributional sense. But this is a bit hand waving here because we haven't seen this or you haven't learned this yet. All right. And one last thing, which I promised to do, is now the notion of Greeks. So just to conclude here, so the Greeks, which you might see financial context, are the partial derivatives of the prices with respect to the parameters and the asset price. So, okay. In financial terms, what do they measure? Well, they measure the sensitivity of the prices and hedging strategies and so on with respect to the variation in the model parameter or the underlying asset. That's what you learn if you ask an economist. Mathematically speaking, how do you measure the sensitivity of a function? Well, you take the derivative and that's what it is. So there's no magic involved. Standard examples of Greeks. The most famous one is delta. They are named, I mean, they're called Greeks because they come, I mean, they're labeled with Greek letters. This is just take your Black-Scholes price and take the derivative with respect to the underlying asset. Yes. And well, that gives you your delta hedging. Delta hedging. This is the replicating trading strategy you need to implement in the Black-Scholes model to replicate your call option. All right. This is the sensitivity, how your trading strategy changes if the underlying asset prices changes. Means you take the second derivative because this is the first derivative of the delta. Since it's a very crucial parameter, you have also vigor, which is the derivative, partial derivative of the Black-Scholes price with respect to the volatility parameter. And this is a very central parameter, as we will learn in the advanced mathematical finance course, in the hedging and pricing of financial options and also trading decisions and so on. This is a very crucial parameter which you care about. And there, of course, much more. Don't worry. This was, of course, a bit fast to follow all details. This was more first glimpse in what comes if we decide to keep doing mathematical finance and going to the more advanced settings. So that's my concluding remark here. If you like to learn more about mathematical finance in continuous time, please visit the lecture course Advanced Mathematical Finance. Doesn't mean you have to do it next term. I mean, it will be offered also in the future. Because I mean, I know those who are in the sixth semester, then this might be more much to ask. But if you at some point want to learn more, I'm happy to welcome you in the Advanced Mathematical Finance course, where we then make these things which I touched here now on the surveys in a more rigorous way and really derive them and study them in detail. All right, I think this is enough from my side. I hope you all enjoyed the course, and I hope you learned also a lot. I will also send out some further information about the upcoming exam, and I will post it also on my webpage, so check them. So by the end of the term, I will give you some details and the sample exams there. Well, that's, I mean, I will inform you about this later on in detail. All right. I wish you all the best.